imagine a population of elderly men. Now that population might consist of hundreds of thousands of individuals. We could consider a scatter plot of an individual's weight versus height. So for example, this point here in the scatter plot would represent an elderly man whose height is given by this x value and whose weight is given by this value here. Now we're dealing with a large population, so I've only shown some dots, but you could imagine that there are hundreds of thousands of dots here. We're going to assume a linear dependence. That means we're going to assume that these points can be fitted by a straight line. Now that's a bit of an assumption, to say the least, but just pretend for now that the data can be represented by a straight line. One of the ideas of linear regression is to try and estimate what this line is. Okay, so this is the line that fits through all the values in the population. So we take a sample because we can work with a small sample. So here we have a sample of 10 elderly men. We can know everything about these 10 elderly men, but as for the population, there's so many people involved that it's not feasible. So from this sample we can try to get what's called our line of best fit and use this line as an estimate for the line of best fit of our population. So these 10 points represented 10 elderly men. The line of best fit is found by getting a line, drawing a line through the data such that we minimize these vertical distances. Well, more accurately, we minimize the sum of the squares of all of these vertical distances. So we just draw vertically from each point to this line and imagine squaring all of these distances. So this, we call this distance A, this distance B, C, D, E, F, G, this one H, this one J, and this one K. So we minimize A squared plus B squared plus C squared plus D squared plus E squared plus F squared plus G squared plus H squared plus J squared plus K squared. So that's how we would find this line, and that's something we don't have to do. We'll usually just try and judge this line by just eyeballing the data and making a good guess as to what the line looks like. But if we were to calculate it, it would involve finding a line that minimizes the sum of the square distances, the squared vertical distances of each point to such a line. So with such a line, we have its equation, so we use this as an estimate for the line of best fit for our population. So you can see for different samples, we're going to get different lines. This is one particular sample of size 10. But if we picked another sample of size 10 from this population, say we picked out 10 points at random and found our least squares line, this line is called the least squares line, then we would get a different line. So it obviously varies with our sample. But the idea is that on average, our least squares line will be a good estimate for our line that fits our population. If such a line is given to us like this, if it's already shown on our diagram, we could try and get its equation. So we won't have to be minimizing all these squares, we won't have to do any of this. But let's just go back and revise how to get the equation of a straight line. Well, to do that, we could pick 2 points on the line and get the slope of the line. And from the slope and one of the points, we can get the equation of the line. 2 key things that we're interested in is the value of y, or the weight in this case. Y is the weight, when x, or height, is here at 160. Well, usually we're interested in what weight is actually when the height is 0, which probably doesn't make any sense for this particular data set. But in general, a line has the equation y equals mx plus c. So c is the value of y when x is 0. If we let x equal 0 in this equation, we have y equals m times 0 plus c. We get y equals c. This is the y-intercept. Now, this value here is not c, because we can see that this is the value when x is 160. C is the value when x is 0. But anyway, if we knew this point 0c, and if we know the slope, then we can write down the equation of a line. What's the slope of a line? Well, I've explained this before. If you pick any point on the line and increase x by 1, how does y change? That's the slope. So increasing x by 1 would mean increasing the height by 1 centimeter. And we would see on average that the weight will actually increase by a certain amount, so the slope is positive. So those are two considerations, C and M, although we can't actually read off C on this diagram because the origin here is not at 0. The process of finding this line is called linear regression. So it's based on an assumption. The assumption is that the population itself is linear, which is not always true, of course, and it's not a great linear relationship here, as a matter of fact. We saw in the previous video that the correlation was plus 0.63, so it's not a strong positive correlation, which indicates that the linear dependence between weight and height is not that strong. So maybe this assumption of linearity in the population of elderly men between weight and height is not so strong either.